Hello everyone, this is Rafiul Hassan. I'm an associate professor in the Department of Computer Science at University of Maine Presque. In my today's talk, I will describe about the binary tree, depth first and breadth first traversal. So this is the outline of my today's talk. I'll introduce the binary tree, then I'll describe about the two types of tree traversal. One is the depth first traversal, another one is the breadth first traversal. Then I will just slightly introduce about some of the other tree traversals, for example, in order, pre-order, and post-order. Then I'll summarize today's talk. A binary tree is a data structure or a special type of general tree where each node cannot have more than two children, meaning each node of the tree might have either zero children or one child or two children. It cannot have more than two children. And each node has an element, a reference to a left child and a reference to a right child. I'll show you the shortcut prototype of this uh, node. So in Java, if you implement the tree in Java, so this class could be a small prototype for a tree node. So in this class, as you can see, so let me use my pen. As you can see that the class name, you can use any name for the class name. So here in this example, I have used the class name as B node or binary tree node. So the data can be any object. So you can use any integer type data, string type data, but in this example, I have used an object type data, meaning it can store any type of values. And it has got two link to the two children. One is the left, another one is the right. So the left link will connect with the left child of the node, and the right link will connect to the right child of the node. So these are the two constructors. You can create an empty binary tree, or you can create a binary tree with one root node first. So this is the Java prototype. So you can implement in Python or other languages as well. So there are different types of binary trees available. One is the full type of binary tree. What is the full binary tree? In full binary tree, every node has either 0 or two children. Nodes do not have only one child in the full binary tree. So this is an example of the full binary tree. As you can see, each of the node of this tree have either two children or zero children. For example, if you consider this node, if you look at my screen, this node has got two children, one and two children. And if you consider this node doesn't have any children. So it in a full binary tree, each of the node has either zero tree like this or two children. There is another type of binary tree available, is called complete binary tree. In the complete binary tree, all nodes are completely filled, that it has two children, except possibly the last node, which should be filled from left to right. So let me give you an example. So this is let me delete the pane so that it clears. So you can see that each of the node of this tree has either two children or, except the last node, it has got only one child. So this is a complete binary tree. You can see that each of the node has got this. If you consider this node has got two children from left to right. If you look, this node, the root node, has got two children from left to right. This is the left child. It has got two children. The right child has got two children. And then if you go down, this left node has got two children. This node has got one child, because this is the last node. So in the complete tree, except the last node, each node must have two children. So that is the definition of the complete binary tree. I hope you understood it. Now these are some example of the binary tree. So if you look at this example is neither full nor complete tree, but it is also a binary tree, because each of the node has got either two children or one child or zero child. So you can see this node has got one child, this node has got one child. So this, we can consider this is as a binary tree, but this binary tree is neither full nor complete, because according to the definition of the full, each node must have 0 or 2 children. Okay, there'll be no node with only one child. Okay, so you can see that 0 or 2, so you can see this node has got one child, so it is not full and it is not complete, because in complete binary tree, each of the node from left to right must have 2 children. Now if you look at this example, this is complete but not full. Why? Because according to the definition of the full binary tree, none of the node have one child. So you can see on the last node has got only one child. So it is a complete tree, because if you look at from left to right, each of the nodes have 2 children except the last one. This example, this tree is a full tree, but it's not a complete tree, because if you look at from left to right, this node does not have 2 children, this node does not have 2 children, so it cannot be a complete tree, but it is a full tree because each of the node has got 2 children. These trees are both full and complete tree because each of the nodes have 2 children, and if you look at the from left to right node, this one, left to right node, left to right nodes, each of the nodes have got 2 children, so we can call this is a full tree and complete tree. So there is another type of trees available, it's called perfect binary tree. What is a perfect binary tree? A binary tree is perfect binary tree in which all internal nodes have 2 children and all leaves are at the same level. That is, if a tree is both full and complete, then the tree is called as a perfect binary tree. Let me give you an example. This is a perfect binary tree. Why? Because if you look at from the left to right, all internal nodes, so these are called internal nodes, this is internal nodes, these are internal nodes, these are internal nodes, so all internal nodes have 2 children. You can see the root node has got 2 children, this node has got 2 children, this node has got also 2 children. So all the internal nodes have 2 children and all leaves are at the same level. You can see all the leaves, so the last node of each of the tree is called the leaf node. So all the leaf nodes have you can see leaves are at the same level. You can see these leaves, this leaf and this leaf and this leaf node are on the same level. So we can call it's a perfect binary tree. And of course, this is also a complete tree binary tree, and it's a full binary tree. Okay. So what are the properties of the perfect binary tree? The property of the perfect binary tree is that the number of nodes at depth d in a perfect binary tree will be 2 to the power d. So let us look at this example. So this is the level number 0, this is the level number 1, and this is the level number 2, meaning the depth. So the depth of this tree at this level, root is 0. The depth of this binary tree at this level is 1 and it is 2. So that is how we compute the depth of the tree. So this depth is d equal to 0. So total number of nodes will be 2 to the power 0, that is 1. If you look at this one, the depth at this level of the tree is d is equal to 1. So total nodes at this depth is 2 to the power 1, meaning total number of nodes in this depth is 2. If you go down, the depth of this level of this tree is 2, and that is why the total number of nodes in this level of the tree is 2 to the power 2, that is 4. Notice that it is in a perfect binary tree. This equation will be followed. So another property of the perfect binary tree is that the total number of nodes in a perfect binary tree, so total number. The previous example was the total number of nodes in each level of at each depth of the tree. This property 2 is the total number of nodes in the whole tree will be 2 to the power h plus 1 minus 1. So this is if we follow this formula, then we can compute the total number of nodes in the perfect binary tree. So if we look at here, what is the h? H is the height, the depth of the tree. In this case, the depth of the tree is 2, because the depth here is 0, the depth here is 1, so depth here is 2. So the depth of the tree is 2. So if we follow the formula, 2 to the power h plus 1, meaning 2 to the power 2 plus 1, minus 1. So it will be 2 to the power 2 cube minus 1. So 8 minus 1. The total number of nodes in this tree is 7. Let us count it. 1, 2, 3, 4, 5, 6, 7. So total number of nodes in this perfect binary tree will be 7 if you follow this formula. So yeah, we can prove it, in this level, how many nodes are there? 2 to the power 0. In this level, how many nodes are there? 2 to the power 1. In this level, how many nodes are there? 2 to the 2 squared. So if I add all these total nodes, it will be 7. So this property 2 is satisfied if we, in the perfect binary tree, if you follow this formula, 2 to the power s plus 1 minus 1. So these are the two properties that belong to the perfect binary tree. I hope you understood it, how to compute the total number of nodes in a perfect binary tree. So what is the complexity of the binary tree operations? So there are three operations that we can consider in the binary tree. One is the searching, another one is the insertion, another one is the deletion. What is the searching? Let us consider I have got a binary tree. I'm looking for a specific node or a specific value in the binary tree. So if we consider this example on the right hand side on your screen, you can see it's a binary tree and there are three nodes A, C, and Q. Of course, this is not a perfect binary tree. This is not a full binary tree, or this is not a complete binary tree. In this binary tree, if you are looking for the node Q, so we have to traverse all elements. For example, we have to consider from the root A, is this the Q? No. So we have to go to the next level of the tree, C. Is it Q? No. Then we have to go to the next level, next child of the tree. Is the Q? Is it Q? Yes. So we have to traverse all the nodes in this tree to find or look for the specific node Q. Therefore, the searching in the binary tree has worst case scenario. If the this node that we are looking for at the leaf level, and if we have to traverse through all the tree, the worst case scenario, the complexity of the worst complexity will be order of n, because we have to traverse through all the tree. Meaning, if there are n number of nodes, we have to travel through all the n nodes to find out the specific node in the worst case scenario. That is why the complexity of the binary tree for searching an element will be order of n, where n is the total number of nodes in the tree. So what is the complexity of the insertion in the binary tree? For inserting element as the left child of Q, so you can insert the element as a left child, like here, or you can insert the element at the right child here, right? So based on the criterion, if we insert the element as the left child of the Q, we have to traverse. If we just add here, then what will happen? We have to traverse all the elements up to n elements to find out the value of Q. Then we can add the new node here. So in this case, or scenario, the complexity of the insertion will be order of n. Of course, the best scenario could be 1, because if we just add at the node number 1, so the best scenario will be order of 1, but the worst scenario will be order of n. Same thing with the searching. If we find the first node is the Q, so the searching, the complexity, best complexity will be order of 1. So in this case, we are considering the worst scenario. Then you can compute the average, best plus worst, that will be the average. Now let us look at the deletion of the node in the tree. How we can delete it? In order to delete any node in the tree, first we need to find out the node in the tree, then we can delete it. For example, we are interested to delete the Q. So first we need to find the Q, then we can remove this Q, we can remove this link, right? We can say that, okay, C does not have any child. So that is how we can delete a node in the tree. So in order to delete in the tree, as you can imagine, that we have to look for the specific node first, then we have to delete it. So the deletion, or the complexity of the deletion from a tree, any element in the tree, the complexity will be same thing like a searching in the tree. So it will be order of n. I believe that you understood why the complexity of the deletion and searching will be the same, because in the deletion we have to look for the specific node first, and the complexity of the searching is order of n, and then deletion will take only one step to delete or remove the link from the tree. So we can ignore that things. As you know that when you studied the complexity, you know that we can ignore some of the things. We always consider the dominating term in the equation in order to compute the complexity of an algorithm. So I think that up to this point, I have just introduced about the binary tree, and I believe that you understood what is a binary tree. As you can, I have defined that binary tree has got uh, at least two children, not at least, maximum two children, not at least, sorry. So it will have maximum two children. So each node of the tree might have 0 children, 1 children, or 2 children. It cannot have more than 2 children. So that is how the binary tree is defined. So now I'll go for the another very challenging algorithm in the binary tree is called depth first traversal. It's a very popular algorithm. So what is the depth first traversal? So in order to traverse the tree, there are two ways you can traverse the tree. One is the depth first, another one is the breadth first. So first algorithm, that is the depth first. In the depth first, it tries to go deeper in the tree before exploring the siblings. What does it mean? Let me give you an example in this tree. So we have got a very complex tree here. You can see that it's a very long tree. It has got the depth of 0, 1, 2, 3, 4. So the depth of 4 tree, okay? Binary tree, of course, because it has got maximum two children. Each node has got maximum 2 children. Okay, so and it is not a full tree. As you can see that this node has got only one child, so it is not a full tree, and it's not a complete tree, because from the left to right you can see the H does not have any two children, and so we can say this is not a complete tree, but it is a binary tree. So let us follow the depth first traversal to traverse this tree. So in order to start the traversing, first in any tree we start from the root node. So here the root node is A. So first we'll first we'll visit the A, then according to the depth first traversal criterion, we'll go depth first in the left child. So first A will go from A to B. Okay, so remember that we are exploring the depth first traversal. So then from B we'll go to the D. So we'll always explore the left child first to go deeper. Then I will go to the right. So from here we'll go to the H. And as you can see, as soon as we are traveling, visiting one node, I'm putting the letter here. So we have already traversed A, B, D, H. Then there is no left child here for this H. So we will go to the right sibling. So we'll go to the right sibling, that is I. And I has got one left child, that is M. As you can see, we have already covered the depth part, the depthmost part on the left part of the tree. Then as soon as we finish the left part of this tree, then we'll go to the right. We'll go little bit of right. So M does not have any children, so we'll explore its sibling, that is N, as you can see. So now from there we'll go back to E, not C. Notice that we will not go to the C, because we always finish the left part of the tree first. Okay, so then this E does not have any children. We'll go back to C. Now we'll go back to C. Okay, why? Because E does not have any children, so then we will go back to the up level of the C on the right hand side. So that will be, it will be C. From C it will go to the again left F, then again left J, then sibling to K. So now K does not have any sibling, so then you'll go back to G, then it will go to the left child L. That is how in the depth first traversal we will always explore the left child up until the depth we reach at the depth of the tree. Then we will explore the sibling of the tree. If there is no sibling, then we'll go to the upper level of the tree to explore this the right child of that node. So that is how the depth first traversal works in data structure. So this is another algorithm is called breadth first. In the breadth first, we will first explore the sibling of the any node, then we'll go deeper. So it will be, I can show you here in this example, explore the breadth, that is all the immediate children of a level before going to the deeper. We will not go deeper first, like unlike the depth first traversal. So here first we will start from A, then we will visit B. B has got the sibling C, we'll explore C, then we'll go to the D. Okay, from D has got the sibling E, then we will go to the on the same level. There is another, and there are two children are here, F and G, so we'll explore F and then G. You can see that we are covering the breadth first, then we'll go to the deeper, unlike the depth first. In the depth first, we'll cover the depth according along with the left child, then go to the right child, right sibling. But here we covered the breadth, then we'll go deeper. So now we'll go cover H. There is another I, J, K, L, then we'll go deeper M and N. I believe that you understood up to this point what is the difference between depth first traversal, breadth first traversal, how does these two algorithms work uh, in the binary tree. Now I will show you the algorithm, how you can implement the depth first and breadth first traversal in any language, any programming language. So this is the algorithm. First, you have to have two stack or queue. So depending on the data structure that you use, you can use the same algorithm for the both traversal problems like breadth first or depth first in the binary tree. So I will explain more in the subsequent slides. So let us initialize two variable. One is the to visit, another one is the visited. So these are the lists, and let us consider initially both of these lists are empty. Then we have got another variable x, and that will be the start node. Then we have to add this start node to the visit list. Then we have to follow this while loop while to visit is not empty. This is, as you know, that this is an, it can be an array, it can be a stack, it can be a queue, whatever, but it is a list. So unless the to visit is not empty, you have to consider x equal to the first the element um, in the to visit, and remove this element from the list, and then add all the children of the x to the to visit list, and add the x, the value that you have taken out from the list, to the visited list. So that is how you have to continue this loop until the to visit list is empty. I'll show you in the next slide how does it work. So see, this same algorithm can be applied for both depth first and breadth first traversal algorithm for the binary tree. So let us first, so this is the algorithm. So I have copied this algorithm from the previous slide here to show how does it work in the depth first and breadth first algorithm. So let us first explore the depth first, and I'll follow this algorithm. How does it work? So there is two variables. One is the to visit, another one is the visited, and both of these two variables are the type of these two variables are list type. Okay, so first initialize the to visit and visited list to empty. Yes, these are the two variables, and the values of the variables that are stored in the list are empty. Now let us take the x equal to start node. So what will be the start node? A. So this will be the x, then add this x to the to visit list. So we are adding this x to the to visit list. What is x? This is A. Okay, now what will happen while to visit is not empty? Yes, to visit is not empty because to visit has got the value A, so the condition is true. So it will go into the loop, and then it will take out this element A from the to visit and add this step, add this element to the visited list. And then what will happen? It will add the children of A. What are the children of A? The children of A is B and C. These two children will be added to the to visit list. Okay, so we'll continue this process like this. You can see that we take the B from the to visit, to the visited, and we add all the children of B to the to visit list. What are the children of B? D and E. Same thing, we take the top element of the to visit list, that is D, and add it to the visited, and we'll add all the children of D to the to visit list. You can see HI. So we'll keep continue like this, and you can see that the visited list follow the depth first. You can see A, first we have visited A, then we have visited B, then we have visited D. As you can see, the visited list shows the depth first traversal of the algorithm. I think you understood it. So let me continue these things. You can see that we are adding H, and all the children of H does not have any children. So H doesn't have any children. So now we'll pop the I, or take the I from the to visit, and add all the children of I, that is mn. So we'll continue like this. I think you understood how does this algorithm applies to the depth first traversal of the tree. Now we will apply the same algorithm for the breadth first. On the right hand side, what will happen? We'll add initially the to visit and the visited list are empty. Then we'll take the top element A and add to the to visit. Then we'll take out the A from the to visit, but we'll add the two children of the A, B, C in the to visit list. Notice that the difference between the breadth first and depth first is that in the depth first we have added the value in the to visit one after another, one after another. Like, I'll tell you later what is this data structure that we are using on the depth first. But in the breadth first algorithm, we are adding the data side by side. You can see A, if I take out A, we are adding the children of A, B, C side by side. Then we take B. You can see that we are taking the B, not the C. We are not taking the top element. We are taking the first element. But here in the depth first, we are taking the top element. So you can see in the breadth first, we are taking out the B, then adding DE. So like these things, we are following the same algorithm that is written here, and you can see that the visited list follows the breadth first traversal. You can see A, B, C, T. Can you see? If you look at the tree, A, if you follow my pointer, A, B, C, D. So it is following the breadth first traversal. So what is the tricks that we are using? That we are using the same algorithm, but it can give us solution for the two problems, like depth first or breadth first. The tricks that I'm doing here is that eventually we are applying the same algorithm, but in the depth first we are using stack. So meaning that the to visit this variable is using the stack data structure type, like the stack is last in first out. That is why I have added the elements one after another on one element on top of the another element. But in the breadth first algorithm, we are using the queue structure. To visit is a queue structure. So queue meaning first in first out. The element that you added first in the list, you have to take out that element first. So that is how we can apply the same algorithm, but if we change the data structure of the to visit, so same algorithm can be applied for the depth first and the breadth first algorithm. I believe that you understood how we can apply this algorithm to solve the problem of the depth first traversal and breadth first traversal on a binary tree structure. So there are different another types of tree traversal approach available. I'm not going to discuss this in today's class. Maybe in the next classes we can discuss these things. One is the in order traversal of the tree, pre-order traversal of the tree, or post-order order traversal of the tree. What is the in order? So in order is that we will first look at the branch tree H, then we will go to the root, left tree, left node, root node, right node, left node, root node, right node. So first we have to go through the depth first traversal up to the depth of the tree on the left child, and we find that the H is the leftmost child of the tree. So we will use the H, then D is the root, then M. That is how we call it in order. So H, D, M, H, D, then once we have got the HD, we'll go to the right child, and we can see that on the right child we have got another left child of the right child, that is m. So we'll go for m I n like this. We'll go for left node, right node, left node, root node, right node. That is called in order. In the pre-order, root node, left node, right node. We'll follow these things, but we'll also apply in this traversal algorithms. We'll apply either depth first or breadth first traversal algorithm to implement this in order, pre-order, post-order approaches. I'm not going to discuss in details about these things. As I told you earlier, that maybe in the subsequent classes we'll discuss about this in order, pre-order, and post-order traversal of the tree, how we can apply the depth first or breadth first algorithm to solve these problems. So in summary, we have described about the tree. Tree is a special data structure for efficient data management. We have introduced what is a binary tree, and binary tree does not have more than 2 children at any node. We have described about the two traversal, breadth first traversal and depth first traversal of the tree, and there are many other type of tree available. For example, binary search tree, heap tree, that I did not discuss in today's class. Maybe in the subsequent classes we will discuss about these sort of trees. So that is all for today's class. If you have got any question, anything, please feel free to send me an email. My email address is md.hasan@main.edu. Thank you very much, and I hope that you enjoyed the class today. Thank you, everybody.